Okay, so hello everyone, welcome to the Dandelion Physics series. In today's video will be about our lesson 2 on the topic 1.1. And before I dive into the contents included in our lesson 2, there will be two things that I'm going to talk before we do that. Okay, so the first thing, Merry Christmas, and the second thing is that we're going to have a brief recap about what we did in our lesson 1. So previously in physics, what did we do? So we talked about the SI unit and the derived unit, So what we talked about is that the SI units are the most fundamental and basic units that you will ever encounter. And then the derived units are being derived from our SI unit. So SI units are foundations or the building blocks of our derived units here. So the combination of those SI units will make up our derived units, and that's what we talked about in our lesson 1. And in this class, we're going to be mainly focusing on only two things, nice and simple, because I don't want to make the video too long. So the first thing that we're going to be talking about is the dimensional analysis. And the second thing that we're going to be talking about is the scientific notation and the metric multipliers. And they sound really fancy, but they are really just simple concepts. And we're going to be starting off with the dimensional analysis. Okay, so here, the dimensional analysis. So what we're doing here is basically that we are messing around with those units that we talked about in lesson 1. And to start off with, let me give you a simple example of what exactly are we doing with those units. So let's say that we all know that so D equals 2 V times T. And in this case, meters equals 2. So let's just write down the units that we have here, the units. So this one is meters, and velocity is meters per second. And remember to write in this form, meters per second, and then times second. So using our exponents rule, so -1 here, and then here is the power of 1. When they combine, they cancels out. So here, meters equals meters, and it means that this is a relatively valid equation that we're dealing with here. And then I'm going to give you another equation or another example here. So let's say that someone one day tells you that the displacement equals to the acceleration times time, and you have no idea whether this equation is valid or not. So what you do now is that you're going to implement your dimensional analysis. And how are you going to do that here? So what we're going to do is that still we're going to write out our units in this equation on both sides of the equation. So here's still meters. And on the other side, so acceleration is meters per second squared, so meters per second squared in this form, and then times the second, which is the unit for time. So here, using our exponents rule, so here, that is 1, so when they are combined, that will be, so here, on the left side is still meters, and on the right side is meter times second to the power of -1. So in this case, the units on both sides, they don't match together. They are not the same on both sides, which means that this equation is definitely wrong. So this is a false equation. So the dimensional analysis here can tell us whether a equation is wrong or not. And when you're in your exam, you'll probably see a question like this. So let's say that a person here, he's standing right here, a person, his name is John or Steve or Jonas, it doesn't matter. So this person here is observing the motion of a ball. So he is seeing this ball moving, and this guy is smart. He came up with his own equation about how this ball is moving, and he states that the force acting on this ball, the F, equals 2. So he said the mass times the velocity times the distance. And here is the question, is this equation worth us to take it as a reference or not? So what are we going to do here? So as usual, we're going to use our dimensional analysis. So we're still playing around with the units here. So on the left side, that will be kg times meters times seconds, seconds to the power of -2. Sorry, I hesitated a bit. And on the right side, that would just be the mass is kg, velocity is meters per second, and the displacement is just meters. And let's see whether the two sides matches together or not. And obviously they don't. So on the left hand side, the kg and the mass. Oh, sorry, that's the meters. Oh my god, my brain's not working tonight. And on the other side is the kg as meters squared and per second. So obviously, oh my god, sorry. Obviously, the two sides does not matches each other, which means that this is a false equation. So we cannot take the equation given by this person here. So this is a wrong equation. So, and that's how we're going to use our dimensional analysis. But however, here's a really important thing that we're going to be talking about here. And let me give you an example. So one day, a person tells you that the net force acting on an object equals to 2 times the mass and its acceleration. And let's see, using our dimensional analysis, whether this equation can be taken as a reference or not. So on the left side, kg times meter per second squared. And on the other side, so since 2 is a constant, so there is no unit for 2. Yeah, so we have to remember that constants does not have units. So on the other side is still kg and meters per second squared. Okay, so from our dimensional analysis, we can see that the units on both sides, they match together, so hooray. So maybe here some people will say that, oh, then this equation is correct because the units on both sides, they matches together. But in fact, this is not a correct equation, and why we all know that as a common sense that F equals to ma. There is no equations in physics saying that F equals to 2ma or 3ma or 4 or 5. No, they're all wrong. F only equals to ma. And that is why we come up with a really important conclusion here, as I wrote here. So here, dimensional analysis can only tell you whether an equation is wrong or not, but it cannot tell you whether it's correct or not. And why is that? That's because constants like 1, 2, 3, 5, like those real numbers, they don't have a unit. So when there are those extra or additional those constants in the equation, so even though from dimensional analysis that we know that the units from both sides they matches together, but however, as we can see in the F equals to ma or 2ma or 3, in that example here, we know that the dimensional analysis can only tell us whether an equation is wrong or not, but it cannot tell us whether it is correct or not. And that's all for the dimensional analysis. And then we're going to move on to another thing that we're going to talk about in this lesson, and that is the scientific notation and the metric multiplier. Okay, so what are we doing? Okay, so let's talk about the scientific notation first. So what we're doing here, what we're trying to do is that we're transforming those long numbers into those neat numbers. So maybe a million, a lot of zeros, and you're just too lazy to write the zeros, so you write it in another form with those neat numbers. Okay, so how does it work? So I have kind of a form here. So a times 10 to the power of b, where in this case, the absolute value of a is greater or equal to 1 and smaller than 10. Which means that a can also be negative. And here we have to know that a must be a real number. It must be a real number. It can't be square root of 2 or square root of 3, those kind of things. And b should be an integer. So your b should be an integer. It can be positive or negative, it doesn't matter, but it has to be an integer. And let me give you an example here. So let's say that a number that is like 4952101. So that's a really long number. So what are we going to do here? We're going to transform it into a neat form. So we're going to transform it. So what I'm going to do here is that I'm going to write 4.952101, and that is within our interval here. Is within the interval that we have restricted for a. Okay, and then it's going to times 10 to the power of what? And we can see here, so 10 to the power of 1, 2, 3, 4, 5, 6. So 10 to the power of 6, and we are done. So we found our A, we found our B. And this is a rather a neat form of writing the thing that we're talking about. And maybe let me give you another example here. So maybe like 2954. So writing in the scientific notation, we're going to be writing as 2.954 as is within our interval times 10 to the power of what? So 1, 2, 3, so 10 to the power of 3. And we are done here. Okay, so that's all from the line today. And if you have any questions, please comment down below. And if you would like to stay tuned for further videos, please click subscribe. And I will see you next time in our lesson 3.